Okay, welcome everyone to a second video on how to catch statistical cheaters. And today we will focus on manipulating the calculations. So if there's a cheater, how we can catch a cheater who manipulates the calculations. Okay, and a friendly reminder, Immanuel Kant and his categorical imperative, always be honest, don't cheat, because it's the right thing to do. Okay. Statistics is a lot about correlation. Okay, correlation tries to find out if one thing impacts another. For example, if a COVID vaccination can impact the severity of the COVID infection, right? So reduce it, right? Or if an increase in gun ownership leads to an increase in shootings. Or if CO2 emissions cause global warming, right? So that's a correlation in a nutshell, and there are very many correlation concepts, right? And we will focus on the Pearson correlation concept, right? It is the concept that is used by 90 to 95% of all statistics analysis, okay? And I have two slides where I walk you through the basic idea of the Carl Pearson correlation model. Okay. Well, first of all, this is an overview. What I'm going to talk about: exploit the linearity limitation. We talk about under and overfitting of polynomials. Correlation does not imply causation. Very popular topic, but important. And I'm going to show how a researcher can manipulate the z-score and how can we see that he did that. Okay, so here are two slides on the Carl Pearson correlation model. We have 4 data points here, 1, 2, 3, 4, and we want to see if the profit margin of Apple has an impact on the Apple price. Okay, so these 4 data points are given, and then we derive with the correlation analysis this regression function. And the first important parameter is the regression coefficient, so the slope of this function here. Okay, and basically the higher the slope, the more statistically significant is the impact of x on y, because if the slope is very steep, then a little change in x has an high impact on y. And if the slope is very negative, we would have a high negative impact. Okay, so beta 1 hat just means that we estimate the slope from these 4 data points. Now, is an important regression parameter. We call it the regression coefficient. And to find this function here, y dash of x, we minimize the sum of the vertical squared error terms. So these error terms we square and we minimize, and I'm sure everyone wants to see a proof of this, which you can find here. Okay. The second critical parameter of the Pearson model is the correlation coefficient. I call it rho. Sometimes it's called R. Okay. So it measures the strengths and the direction of the linear relationship. Okay. And we have a covariance term here, which is this here. Okay. And here's a nice graphical representation of the correlation coefficient. You can see if all the data points are on one line, the correlation coefficient is 1. And if the data points disperse more and more, here they're kind of in a circle, then there's no correlation here. And if the data points are on one line and we have a negative relationship, then the correlation coefficient is -1 here. Okay, so that's the second critical parameter that we will work with in this video. Okay. And here's the relationship between the regression coefficient, the slope, and the correlation coefficient. And you can see here if the standard deviation of y and x are the same, the regression coefficient, or the slope, is actually equal to the correlation coefficient. Okay, so that was in a nutshell the Carl Pearson correlation model. Okay, topic number 1, exploiting the linearity limitation of the Pearson model. Unfortunately, the Carl Pearson correlation model can only evaluate linear relationships. Okay, Certain nonlinear relationships cannot be evaluated with a linear Pearson correlation model. And here we have a parabola, right? So y equals x squared. And if you run a correlation analysis with the Pearson model, you get nonsense, right? You get a linear horizontal regression function, and you can see the correlation coefficient is 0. So the Karl Pearson model cannot handle this nonlinear relationship at all. Okay. And here's another example. If we have an inverse parabola, which can be replicated with a tax rate and the tax revenue. So the question is the tax revenue, so the money that the government makes, a function of how much tax it charges? And we have typically this function here. So if the tax rate is 0, there's no tax revenue. If the tax rate is 100%, then there's also no tax revenue, because individuals will stop paying taxes or evade the country, leave the country, right? Okay, so we have this mountain-shaped function here, and if we run the Karl Pearson correlation model on it, we get nonsense again, right? We get a linear horizontal regression function. The correlation coefficient is 0, and that doesn't make any sense. Okay, so this shows that the Karl Pearson model cannot handle certain nonlinear relationships. Okay, so a statistical cheater could argue there is no relationship between tax revenue and the tax rate because the correlation here is 0. But that's of course not true. Okay. How to catch linearity cheaters? Well, observe the graphic visually. Only if the data is approximately linearly distributed can the linear Pearson model be applied. Okay. If the data is nonlinear, the Pearson model, typically underestimates the correlation, so it results in lower correlation than the correlation actually is. Okay. And if the data is nonlinear, apply a nonlinear regression function called polynomial fitting, which we will do right now. Okay. So let's talk about topic 2. Polynomial under and over fitting, and here I just explain what a polynomial is. It's a simple mathematical expression that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents. So this is a polynomial, but x to the power minus 2 is not, because this is a negative exponent. Okay. What is underfitting? It's using a regression function which is not complex enough to capture the relationship between the variables. What is overfitting? The opposite, using a too complex regression function which does not represent the general relationship well. Okay, let's look at some examples. Here actually we have the CO2 emissions globally from 2010 to 2020. This is the blue function with the dots, and then I fitted a linear correlation function, regression function through it, and this area here is the forecast because we have data until 2020. So if I fit a linear regression function through it, I forecast an increase in CO2 emissions beyond 2020. However, if I fit a second-degree polynomial through it, you can see the forecast is negative. If I fit a third-degree polynomial through it, forecast also negative, and a fourth-degree, a fifth-degree actually polynomial also says that the forecast is negative, meaning we're forecasting that CO2 emissions actually decline. Okay. Okay, so we have a big outlier here in 2020 because we had the COVID crisis and it led to an economic recession and we had less CO2 emissions, right? And if you have an outlier like this, I discussed it in the first video, you can't just ignore it, right? It's a part of the data. It's part of the data set and you can't ignore it. But what we can do is, well, if we really have a researcher who anticipates or forecasts a decline in CO2 emissions due to this outlier here, we can use more data, right, which will decrease the weight of the outlier. Okay, and that's what we did on the next slide. Here we have 11 years of data, and in the next slide we will have 41 years of data. Okay, so if you have a researcher who overfits the data, use more data. And also you can use out of sample data, so data that was not used in the original study. Okay, and you can see here if we fit a second degree polynomial now, later data is also enters the regression function, and we have an increase, a forecast that increases CO2 emissions, and same with the third degree polynomial. CO2 emissions are forecasted to increase. Only the fifth degree polynomial here decreases in CO2 emissions, so forecasts a decrease. No? So what have we done? We have used more data, which reduces the weight of the outlier and shows that in the long run, CO2 emissions, unfortunately, are increasing. Okay, so in order to reduce the weight of an outlier, we can use more data and out of sample data. Okay, which gives us typically more rigorous results. Okay. Big question, if we extrapolate a time series, so forecast, or a functional relationship, which order of a polynomial should we use? And the answer is, if we believe that older data is as relevant as newer data, we should use a lower degree polynomial, like over here. So if we believe that older data is as relevant as newer data, we can use a lower degree polynomial. Here I actually use a first degree polynomial, so a linear function. And if we believe more recent data is highly relevant, we should use a higher degree polynomial. So this would weight the more recent data more, and we would actually forecast a decrease. Okay. How to catch under and overfitters? Out of sample testing, right? So test the hypothesis with out of sample data with respect to the time frame and the location. Okay. And as we did, use more data, which reduces the weight of the outlier. Observe visually if the function represents the data points well, right? So see what is a better fit, a linear or nonlinear regression function. And if there's an outlier, what we can also do is conduct a qualitative analysis, right? So ask us, is the reoccurrence of that outlier likely? And evaluate the possibility of the outlier reoccurring. And in the COVID crisis of 2020, we can argue, well, the last big economic impact of a pandemic was pretty much 100 years ago, 1920, with the Spanish flu. So we can argue this outlier is a rare event, right? So we can also evaluate the regression function and the outlier qualitatively, okay? Right, so this outlier here occurring is a rare event. Again, we can't just ignore it as part of the data set, but we can argue it's an unlikely outlier to reoccur. And we can use a lot of data, and then this outlier weight will be reduced. And a researcher who forecasts CO2 emissions declining, we can prove him wrong, right? If we use a lot of data, which again decreases the weight of the outlier. Okay. Third topic, correlation does not imply causation. A very popular topic, but an important one, so I got 2 or 3 slides on that one. What is nonsense correlation? Also termed correlation does not imply causation. Definition, a term used to describe a situation where 2 variables, x and y, are correlated without being causally related to one another. No? And you can buy t-shirts if you feel like it on that topic. Okay. Example of nonsense correlation. Here we have the green function here, which is US spending on science, space, and technology. And the red one is suicides by hanging, strangulation, and suffocation. And you can see they are highly correlated, right? But of course, they're not causally related, right? The green function, US spending on science, doesn't cause suicides. And suicides by hanging, strangulation, and suffocation don't cause more US spending, right? Okay. And there's a, this is from the webpage of Tyler Vegan. You find a lot more examples of nonsense correlation there. He even wrote a book about it if you want to read even more about this. How to detect nonsense correlation cheaters? Well, the Pearson correlation model does not include any methodology to determine the existence or the nature of a causal relationship between the variables, right? That's the way it is, right? So what do we have to do? Therefore, to catch nonsense correlation, we have to exogenously, so from the outside, determine the existence of a direct or indirect causal relationship between x and y, and secondly, the direction of that causal relationship. Does x cause y, does y cause x, or do they cause each other? No? This is what we have to do before we do a Pearson correlation study, right? How can we do that? Well, we look at the theoretical analyses. If there is some theoretical analyses, if x causes y or y causes x. And we can rely on empirical observations and see if there's any support for the claim of the researcher. Okay? Have a critical mind. So if a researcher claims something that doesn't really make sense at all, so for example, that vaccinations cause autism, there are some who claim that, but there's no scientific evidence for that claim. And even though there might be a correlation between vaccinations and autism, because both have increased in time, there's no causal relationship between them, right? So have a critical mind and use common sense, okay? Okay, so that was already correlation does not mean causation, and that's an important limitation of the Pearson model. And again, before you do a correlation analysis, point 1 and 2 have to be satisfied, okay? Okay, last topic for today, manipulating the Z-score. The idea is to find if a result is statistically significant, okay? So here we have the normal distribution, and here's the right tail, 5%, if we use a 95% confidence level. So for example, you take a test with the 99 other students, and your score is 98. So then you fall in this right tail here, and then you can brag about how smart you are, because you are statistically significantly smarter than the other test takers, right? Because you fall in this significant right tail here, okay? And we can also calculate if you fall into the right tail. Here's an example. Jeff is very proud of his height and wants to prove to his girlfriend that he is significantly taller than the average US male. Jeff is 180 centimeters tall. I'm using centimeters here since it is my goal in life to introduce the metric system to the US, which is not possible, right? To use the Z-score, Jeff has to estimate the average US male height, which is not precisely known. Jeff asks 30 male students and calculates the average height of 177 centimeters. In addition, Jeff has to estimate the US population male height standard deviation. After some research, he assumes it's 15. And then he throws all the data into the Z-score, and this is our Z-score here. And this is the sample mean, okay. This is the, so 180 actually, we only have one student or one person. Jeff, this is the population mean, which is our 177. So actually this is estimated, right? Here's the population standard deviation, which is also estimated, and n is the sample size, and we have 30 as the sample size here. Okay, so if Jeff throws all these numbers into the z-score, we get 180 minus 177, and 15 is the standard deviation, and we get 1.095. Believe me, it's right there. It's right behind my big forehead. Okay, so I think I have it on the next slide too. Yeah, here's the result of the example, and what does that mean? Since 1.095 is lower, then I should put here, and then the critical value of 1.645. Right? It follows that Jeff is not statistically significantly taller, right? Because this number is not in the right tail. In the right tail are only numbers that are bigger than 1.645. Okay? However, now what can happen is that Jeff can quite easily manipulate the parameters, right? The population mean, especially the population standard deviation, and the sample size to manipulate the z-score so that it is bigger than the critical value of 1.645. Okay. For example, if Jeff increases the sample size from 30 to 70, so n increases from 30 to 70, he now gets that the z-score is 1.673, which is bigger than the critical value of 1.6445. And it's even easier to manipulate the population mean, which is often not known, and especially the population standard deviation. This is also called a nuisance parameter because it's difficult to evaluate, right? And so it's quite easy to manipulate these three variables here to derive a z-score which is statistically significant. Okay. How to catch z-score manipulators? See if the researcher has justified the parameter values of the z-score, right? So especially this one we cannot manipulate because this is the mean of the sample, and we know that. In this case, it's just 180 because we have one sample, which is Jeff. Okay, but these three can be easily manipulated, right? Okay, so see if the researcher has justified the parameter values of the z-score. Okay, with respect to the sample size, n, a too small sample size means little statistical rigor. A too large sample size inflates the statistical significance, which I just showed with the example. So the bigger the sample size, that increases the z-score, right? Okay. And there's some logic to that, that basically a bigger sample size increases the z-score. The bigger the sample size, actually the smaller the difference between the sample mean and the population mean, right? If n goes to infinity, or n goes to the total number of population, then this would actually be 0. The difference would be 0 because our sample is the population and the sample mean is the population mean. So there's some logic in letting the sample size, the bigger it is, increase the z-score because this difference gets smaller and smaller if n gets bigger. Nevertheless, as we showed in the example, the bigger n, the bigger the z-score. So we can fairly easily manipulate the z-score with an increase in the sample size. Check the parameter values yourself or let your unpaid intern do it. Okay. Okay, conclusion. Numerous ways to manipulate the statistical calculations exist. The Pearson correlation model typically underestimates nonlinear correlation. So for example, we have the parabola as we had in the first slides. The correlation will be 0, and that is very misleading because there is a relationship between y, and x. No? Look at the data to see if a linear or nonlinear correlation approach is warranted. With the z-score, statistical significance is quite easily achieved by manipulating the parameters. See if the researcher has justified his or her choice or the calculation of the parameter values. Okay, that was it. Here, if you want to read more, is a really, really good book. Thank you, and I think I'm giving you my email here too if you have further questions. Okay, thank you, over and out.